Welcome to today's Explainer. We're diving into something absolutely crucial in the industrial world: energy balance in a chemical process plant. Think about these gargantuan facilities for a second. They're processing massive amounts of energy every single day. Today, we're going to demystify exactly how engineers track, calculate, and ultimately optimize all that power. So whether you're an engineering student, a seasoned pro, or just curious about how these massive operations run without going completely off the rails, let's jump right in.
Okay, here is our roadmap for today. Number 1, the master energy equation. 2, identifying the energy inputs. 3, tracking the energy outputs. 4, calculating the heat duty. And 5, why energy balance matters. So let's start with a really massive question, right? How do massive chemical plants track literally millions of dollars in energy? I mean, you can't just slap a meter on every single pipe and call it a day. I want you to think of a chemical plant not just as a crazy labyrinth of pipes and reactors, but as a giant financial ledger. Just like a massive corporation requires a meticulous audit to balance its financial books down to the last penny, a chemical plant requires an energy audit to balance its thermal books. If energy is currency, process engineers are basically the forensic accountants, making absolutely sure nothing goes missing.
Section 1. The Master Energy Equation.
All right, here it is, the absolute golden rule of process engineering. Energy in equals energy out plus energy accumulation plus energy losses. It is so brilliantly simple, yet it dictates literally everything. Think of the energy in as your plant's income. Obviously, this income has to perfectly match your expenses, which is your energy out. But sometimes energy is stored within the system, Maybe a huge tank is slowly heating up over time. That's your energy accumulation. Kind of like putting money into a savings account. And lastly, you have energy losses. This is the money that falls right out of your pocket onto the street. Think of heat escaping from uninsulated pipes straight into the cold winter air. Every single joule of energy has to be accounted for in this equation.
To actually utilize this master equation and balance those books, process engineers rely on a standard 3-step diagnostic method. Step 1 is to painstakingly identify all the energy inputs. Step 2 is to track down all the energy outputs. And Step 3 is to calculate the heat duty, which basically means figuring out the actual mathematical values of these energy transfers. This method right here is the true bread and butter of plant optimization.
Section 2. Identifying the energy inputs.
Section 3. Tracking the energy outputs.
When we contrast these two sides of the ledger conceptually, a really clear picture starts to emerge. For our inputs, our deposits, we're pumping in steam, we're burning fuel or natural gas, pulling electricity directly from the grid, and circulating hot oil or thermic fluid. We even count cooling water and the sensible heat of the raw feed materials just entering the reactor. Conversely, our outputs, the withdrawals, include the heat carried away by the final product, the steam we actually consumed or generated, the heat removed by that cooling water, the hot or cold streams leaving the system, and crucially, heat losses to the atmosphere and general equipment losses. The fundamental point is this: if the inputs don't perfectly match the outputs, you have a massive leak in your ledger. That missing energy is either accumulating dangerously inside your system or it's bleeding out into the atmosphere, which is costing money by the minute.
Section 4. Calculating the heat duty.
Okay, let's break down the math in plain, accessible language. When engineers calculate heat duty, which is represented by the letter Q, they are generally looking at two scenarios: sensible heating and phase changes. For sensible heating, which just means changing the temperature of a substance without boiling it or freezing it, the formula is Q equals M times Cp times delta T. M is the mass flow rate, basically how many kilograms per hour are flowing through the pipe. Cp is the specific heat. I like to think of this as how stubborn the material is to heat up. Water, for instance, is super stubborn. It takes a ton of energy to raise its temperature. And delta T is simply the temperature difference, how many degrees you're actually trying to raise or lower it. Now, on the other hand, if you are boiling a liquid into a gas, well, that's a phase change. The formula shifts to Q equals M times lambda, where lambda is the latent heat. That is the massive burst of energy required just to change the state of the material, completely separate from changing its temperature.
Let's see how this builds into a real-world word problem so we can audit a specific transaction in our energy ledger. Imagine a plant needs to heat 10,000 kilograms per hour of a liquid chemical from a relatively cool 30 degrees Celsius up to a scorching 150 degrees Celsius. We'll assume the specific heat, our Cp, is 2 kilojoules per kilogram Kelvin. If we plug this right into our sensible heat equation, we get Q equals 10,000 for the mass, multiplied by 2 for the specific heat, multiplied by the temperature difference. And that difference is 150 minus 30, which gives us 120 degrees. So 10,000 times 2 times 120.
The result is 2,400,000 kilojoules per hour. But, in the engineering world, we usually prefer to talk in kilowatts to really understand the power demand. When you convert that 2.4 million kilojoules per hour by dividing by the 3,600 seconds in an hour, you get our final theoretical heat duty, right around 667 kilowatts. That is the exact amount of continuous energy power you need to deposit into this system to make that temperature jump happen.
But wait, and this brilliantly illustrates the gap between the classroom and the control room. That 667 kilowatts is purely theoretical. It assumes a completely perfect universe. In an actual, messy, real-world plant, operators always have to account for friction, for wear and tear. They have to consider equipment efficiency, like, is the boiler actually running optimally? They have to look at heat losses and insulation condition. Because if the fiberglass insulation on that pipe is degraded, a big chunk of that 667 kilowatts is just going to heat the air outside. To actually achieve 667 kilowatts of heating inside the liquid, the plant might have to generate something like 800 kilowatts at the source just to make up for all those utility and transport inefficiencies.
Section 5. Why energy balance matters. Doing all this meticulous math is exactly how you cure plant inefficiencies. Let's run through the critical operational and financial benefits here. First, utility optimization. By balancing the ledger, you stop overproducing steam you just don't need. Next, you can directly track boiler and thermic fluid heater efficiency. If you're putting in way more natural gas but getting less heat out, you know for sure it's time for maintenance. It also allows you to monitor heat exchanger performance, making sure they aren't getting fouled or clogged up. By identifying energy losses, like those degraded insulations we mentioned, you are directly reducing production cost. Every single kilowatt saved is a penny earned. And all of this culminates in a massive improvement to overall plant efficiency.
I want to leave you with this really crucial takeaway. A good energy balance doesn't just tell us how much energy we use. It tells us where we can save it. Tracking energy isn't just some academic exercise in mathematics. It is the absolute ultimate tool for discovering, hitting financial value, and driving industrial sustainability. So the next time you look at a massive industrial facility, ask yourself, are their thermal books meticulously balanced, or is enough energy to power a small city just quietly vanishing into thin air? Thanks for joining me on this explainer, and keep asking great questions.